Is it audible? My sound is clear to everyone? Okay, how we can prepare, this was the last topic we just started, how we can prepare a salt or preparation of the salt. So the reactions of acid can be used to prepare the soluble salts, and there's another method which we call ionic precipitation. The definition of a salt: when hydrogen of an acid is replaced by a metal, we call, or ammonium ion, we call that as a salt. Like example, hydrochloric acid is HCl, but in place of this H, if I replace with any metal, like example sodium, then it will we call that as a salt. Or hydrogen is replaced by calcium, so it will form calcium chloride. This calcium chloride is also a salt. So when hydrogen of the acid is replaced by a metal, we call that as a salt. If we want to prepare chloride salts, we use hydrochloric acid. If we want to prepare nitrate salts, we use nitric acid. And if we want to prepare sulfate salt, so we will use sulfuric acid. How we can carry out a reaction? As we know, we can use acid-base reaction. So hydrochloric acid react with sodium hydroxide, gives NaCl plus water. But this sodium chloride is a soluble salt. So how we obtain this soluble salt? We can use crystallization or evaporation. But before that, because acids are aqueous and colorless, alkalis are also aqueous and colorless, so we cannot identify which one is more, whether acid is more or alkali is more. So for this purpose, we use a titration, a technique in which we find the concentrations or volume of unknown substance by a known one. So what we will do, we will take a conical flask, and by either using a pipette or a measuring cylinder, we will transfer solution into a conical flask. So example, we fill the measuring cylinder. Example, we fill the measuring cylinder with acid. It can be any acid, hydrochloric acid or nitric acid. In this example, we are using hydrochloric acid, so we use a measuring cylinder and we measure the specific volume of hydrochloric acid and transfer that into a conical flask. Then the second step, we add indicator. Indicators are weak acid which show different colors in different medium. So phenolphthalein, if you use phenolphthalein, it will be colorless. So example, if you use phenolphthalein, add indicators, but it should be drops of indicator, not too much. Only few drops are enough. So when we add drops of indicator, example, if phenolphthalein is there, it will remain colorless. Then we will fill the burette with an alkali, and we transfer the alkali or add alkali to a conical flask which is filled originally with acid. So once all of the acid used up, then no more acid is left. So acid plus alkali was giving salt and water. So once all of the acid is used up, no more acid is there. So we are left with the alkali, and the indicator will show a color change. The moment indicator will show a color change, we can identify or record the volume of alkali used for this reaction. So if we using a measuring cylinder, we use 10 cm cube of acid, and we'll read the lower meniscus and identify, like example, read the original volume and final volume. So example, 10.3 cm cube of alkali was needed. So we'll repeat the experiment without an indicator, and then from a salt solution, we will obtain a salt by using either crystallization or evaporation. Is it clear, this technique, how to obtain a soluble salt by acid-base reaction or acid-base titration? Any doubt in this? Then this other methods, we can use acid plus metal, which gives salt and hydrogen. So we use excess of metal until no more. This method is same for either adding acid. If there is more alkali, if it is a small amount of alkali, then it will be light in color, it's pink in color. So the second method which we can use to prepare this salt, we can use acid plus metal or acid plus metal carbonate. Both techniques use the same concept. So we'll have a container, example a beaker, and this beaker is filled with acid. Using a spatula, we add small quantity of the metal in the beginning. We'll add a metal when we add a metal, what we'll observe the solid dissolve and bubbles or fizz. The solid dissolve because the metal is reacting, and bubbles are due to the presence of hydrogen. And we'll make sure that all of the acid used up. So how we'll make sure all of the acid used up until no more bubbles form? So if no more bubbles form, it means all of the acid is used up. So when all of the acid used up, we will remove the unreacted metal by filtration, and then we carry out crystallization. So this method is valid for both metal, react with acid. It is for metal carbonate as well. Or it is valid for metal oxide. But in case of metal oxide observation, it does not give any bubbles. So if you observe that a solid which you are adding is not reacting, or the size or amount of solid which you are adding is not changing, it shows that metal oxide is in excess. And in case of metal oxide, because the reactions are very slow, so we have to warm the acid first as compared to when metal or metal carbonate react with acid. Just now we discussed how we can prepare. As we discussed now, for example, if you are using insoluble base such as metal or solid metal carbonate, so these are the steps, because this is related to paper 4 as well. Sorry, unit 1. Unit 3 is a ATP, alternative for practical, but unit 1 also you find some question in which you have to plan experiment to prepare a salt. So first we add a solid base to the acid, filter off the excess of the solid base or metal carbonate, then heat the filtrate solution until the volume reduced to half, and then we will cool down the solution and leave the solution and allow remain water to evaporate slowly and crystals to form. Filter and pick out the crystals and dry, leave to dry, or put the crystal between the filter so that it will be dry. But this will not give 100% yield. Why this will not give 100% yield? Because what happened first, when an acid reacted with a metal, it formed a salt solution. So during filtration, some of the salt solution left on the filter paper. That's why it will not give you 100% result. So the percentage yield of the crystal will always be less than 100, because some salts stay in the solution, and there is also some loss on transferring from one container to another, and there's a loss on filtrate. So these are the things which occur. If using a soluble base, for example, we are using acid base, so we will use indicator for this purpose and repeat the procedure without indicator. For insoluble base, or which is also called ionic precipitation, by mixing two soluble salts, if a solid is formed, this type of reaction is called ionic precipitation. So example, you're mixing lead nitrate with sodium chloride. So what we'll do, we'll take equal concentration. Like if a concentration of lead nitrate is 1 mole per dm cube, the concentration of sodium chloride should also be 1 mole per dm cube. So when the two salt solutions have the equal concentrations, the ratio of the moles is same as the ratio of the volume required for a complete reaction. So what we will do, if I took 5 cm cube of lead nitrate, according to equation, this amount of sodium chloride, for a balanced equation, you can see amount of sodium chloride should be twice. So if 5 cm cube of lead nitrate is there, then it means 10 cm cube of sodium chloride is needed. So when we mix these two solutions, suddenly a solid is formed. So what we and there will be another salt, but that other salt is a soluble salt. So we don't observe anything for that salt. Only the solid which is formed when mixing two solutions, we call that as ionic precipitation. And this solid, what we can do, we can filter it and just simply dry by using a filter paper. If you want to write an ionic equation, so first we cancel out the common ion in aqueous substance. So nitrate is common both sides. That's why we can cancel out nitrate. Chloride, one side it is aqueous, the other side it is solid, so it cannot be. Sodium is aqueous both sides, so it can cancel out. So what you're left with, you're left with lead ion. You can see a lead ion. You're left with two chloride ions. That's why two chloride ions, and it gives lead chloride, which is a ionic equation. The ions which you cancel out, the ions are known as spectator ion. Why we call spectator ion? Because originally they are not taking part or not causing any change in the reaction mixture before and after. Before also they are aqueous, after also they are aqueous, so they remain in the solution, so does not uh, carry out any change during a chemical reaction. So we call them as spectator ion. Is it clear? The formation of ionic this insoluble salt by ionic precipitation. So mixing two salt solutions result in a formation of insoluble salt or solid. Is it clear? Any doubt? When you mix two solutions, like example, you have lead nitrate, aqueous lead nitrate, and the other one is sodium chloride. So two solutions are there, colorless solutions. One is for the lead nitrate and the other one is for sodium chloride. You mix them into another container. When you mix them into another container, what you observe, you will observe that the two solutions, the moment they mix with each other, they will form solid. And that solid is actually lead chloride. Lead chloride is a yellow precipitate, so you will observe yellow solid. So lead chloride will be there and sodium nitrate solution is there. How I can separate this lead chloride from sodium nitrate? So we can simply do filtration. Is it clear now? Then different reaction, we can write an ionic equation. Like example, the first, hydrochloric acid is reacting with magnesium. So when magnesium react with hydrochloric acid, give magnesium chloride plus hydrogen. So what we'll observe bubbles. When we write the state symbol, all acids are aqueous, metal solid, magnesium chloride aqueous, because you have to recall that table, that all nitrates are soluble, most chloride except silver, mercury and lead. Most sulfates are also soluble except barium, calcium and lead, and most carbonates are insoluble except sodium, potassium and ammonium carbonate. So if you want to write an ionic equation, what we'll do first, we'll cancel out the common ions in aqueous. So chloride ions are common, so we cancel out chloride ion. So what we are left with, we are left with 2 hydrogen ion. You can see 2 hydrogen ion. Magnesium is solid, so solid, liquid and gas will not change. We write as it is. Magnesium chloride is aqueous, so it means it contains magnesium ion, and hydrogen is a gas, so it is a molecule. Another equation, nitrous acid react with barium hydroxide, gives barium nitride plus water. So aqueous, so nitrous, nitrite ion, cancel with nitrite ion. Barium is aqueous, so that cancel out each other. So what you're left with, 2 hydrogen ion and you're left with 2 hydroxide ion. And so means I can write like this: 2 hydrogen ion plus 2 hydroxide ion give 2 water molecule. Or 2 is the simplest ratio, so 1 is the simplest ratio, so I can cancel out. All salts are not aqueous. You have to recall that table. In O levels, you studied this table, that in O levels, you studied this table, salts which are soluble, all nitrates. Salt, if salt are in solid state, but if we add water, if you have a salt, all the salts are in solid state, but if we add water, then some of the salts will dissolve or they will become aqueous, and some of the salts will not dissolve or they will be solid or precipitate, you can say, if it is formed during the mixing of two salts. All nitrates are soluble. Most chlorides are soluble. Most sulfates are soluble. And most carbonates are insoluble. But the 3 of the salts which are not soluble, all nitrates are there, but 3 of the chlorides which are not soluble, silver chloride, mercury chloride, and lead chloride. These are the 3 salts which are not soluble. Most sulfates are also soluble except 3. Barium, calcium, and lead. And most carbonates are insoluble except 3. Potassium carbonate, sodium carbonate, and ammonium carbonate. So these three carbonates are soluble carbonates. So you have to learn, this is the same table you took, so you can identify whether they are soluble or insoluble. So when we add water, then we discuss like whether it will dissolve. So we'll say aqueous. If it does not dissolve, it means it will remain insoluble. Then what is the difference between a hazard and the risk? So hazard is a substance or a procedure that has a potential to do harm. Like something, it can be a substance or it can be a procedure as well, which has potential to do harm or can harm you. We call that as hazard. Like example, something is toxic. So toxic is a hazard. Something is flammable, can catch fire, hazard. It's harmful to use, so may hazard. Irritant to eye or skin, corrosive, oxidizing or carcinogenic. It means can cause cancer or can lead to cancer. So hazards are there. For when you are using any compound, certain hazards are there related to the compound. But risk is the probability or chance that harm or will result from use. Like example, if you are using, risk can be changed. Like you can minimize the risk, but you cannot change the hazard. If something is toxic, it will remain toxic. But you can minimize the risk. So this is a probability or chance that will harm you. And there are different ways by which you can minimize the risk. So in a lab, we try to we can minimize the risk, but we cannot change the hazard. So for example, if something is irritant, like dilute acid and alkalis, they are irritant. Irritant is what? Irritant is a hazard. But what you can do means it can cause a harm. So what you can do, you can wear the goggles and minimize the or reduce the risk, the potential to cause a harm. Corrosive, like strong acid and strong alkalis are corrosive, so you should wear gloves, goggles or lab coat. So why we wear gloves, goggles or lab coat? So we reduce the or minimize the risk. If something is flammable, like such as organic compounds, they are flammable, so we should keep away from a naked flame or directly, we should not expose them to a flame. Toxic, if something is toxic, wear gloves, avoid skin contact, wash hand after the use. If something is oxidizing, oxidizing means also easily oxidize the material or can catch fire as well. So we should always keep away from flammable things or because it can easily oxidize the material. So these are the things which we are carrying out. Why it is important to learn these factors, so that you can identify that what precautionary measure or safety measure you should take to minimize the risk. Hazard cannot be minimized. Hazard is there, but risk can be reduced or minimized. Then hazardous substance in a low concentration, like if something is having a hazard, like it is toxic, so we should use low concentration or low amount, so it will not pose the same risk as their pure substance. For example, if you are using acid in the lab, so what we prefer to use concentrated acid or dilute acids in the lab. What should be our preference? Use concentrated acid or dilute acids? So we should prefer to use dilute acids. Why? Because the concentrated acids are corrosive, so they are harmful, they have hazard. So we reduce the risk that they can harm us by using a dilute acid. Is it clear, this concept? Any doubt in this? Then different apparatus can be used depending on what is the purpose. Like example, if you want to collect a gas, or you want to measure the volume of the gas, or you want to measure the speed or the rate of the reaction, so gas syringe can be used for a variety of experiment where we want to measure the volume of a gas, and using volume we can work out the moles. The volume of the gas depends on the pressure and temperature. So when the recording volume, it is important to note down the temperature and pressure of the room. Because, for example, if you carry out experiment at 25 degrees centigrade and the similar experiment with the same amount of reactant, you are carrying out at 40 degrees centigrade, you will not have the same final result. Why? Because at higher temperature, the molecules of a gas move away from each other, or gas can expand. So it is important that you note the surrounding temperature as well, as the volume of the gas is affected by temperature and pressure as well. Then using this, we can, using the volume divided by 24, what we will get? We'll get moles. And using the moles, we can work out the equation moles for other substance and unknown substance as well. What are the errors which are associated here by in using a gas syringe? A gas escape before the bung inserted. Like this bung, when we insert, maybe a reaction started and the gas might escape. So that's an error. Syringe stick, because this is the syringe of the gas might stick, so it will lead to an error. Some gas like carbon dioxide or sulfur dioxide are soluble in water. So what happened? Maybe a gas which is released here will dissolve in a solution. So we will not get the same amount of a gas which is released if it's a soluble gas. So it will not be accurate. Is it clear? So these are the errors associated by in using a gas syringe. Then making a solution. If we want to make a standard solution, so what we can do, how we can make a standard solution, because the concept is, if I have the moles divided by volume, what I'll get concentration, that's moles per volume. So for this purpose, or mole per dm cube, for this purpose we should know the moles exactly, and we should know the volume exactly. How to find the moles? If I want, example, I want to make a standard solution or a solution of a known concentration for sodium chloride. So first what we do, we measure the mass of a solute in a weighing bottle. So how we can measure the mass? We can have a balance and we place this solid on the balance. So we place this solid on the balance and we'll know the mass of this, like example 30 grams. So we have 30 grams of sodium chloride. Using this mass, we have the mass, we can find the moles. Moles is equals to mass divided by mass in gram divided by molar mass. Molar mass of sodium chloride is 58.5, so we get the moles. How to get the volume? So what we will do, for this purpose, we will use a volumetric flask. This flask is called volumetric flask. This volumetric flask is having only one label. So we add a distilled water or deionized water until we reach the label, and we shake the bottle so that all of the solid will dissolve. So we have the volume also, what volume we took according, normally we use 250 cm cube volumetric flask. So this is 250 cm cube, we'll convert into dm cube, which is 0.25 decimeter cube. So we have the volume of the solution, we have the mass of a solute, moles, the concentration is moles of a solute divided by volume of a solvent. Using this, we get the concentration of a solution formed. Is it clear? Then what are the errors associated with the different apparatus? It depends. So errors, a percentage error is the smallest value or sensitivity error or a least count divided by measurement made multiplied by 100. But if you are reading the apparatus twice, then the error will be multiplied by 2. Like example, if you are using a burette and original volume or the beginning, the start of experiment, say the volume was 10.2. Once you remove some of the liquid out, some of the liquid, as you remove, the volume will decrease. Say it's 15.4. So what is the volume of the liquid which you remove or use for the experiment? It's 15.4 minus 10.2, which is equals to 5.2 cm cube. So 5.2 cm cube is a calculated value. If I need a percentage error here, so percentage error is the smallest value. Normally the smallest value which our burette can record, it can vary, like here it's given 0.15, but normally it's 0.1. So smallest value is 0.1. Divide by value recorded is 5.2 multiplied by 100. But this will not be accurate. Why this is not correct? Because in case of burette, I have to read the level twice. I have to record the initial volume and then I have to record the final volume, and the difference in the volume is giving me the volume of a solution which we used. So that's why this error, the smallest value, should be multiplied by 2. So if you are reading the apparatus twice, it should be multiplied by 2. If you are reading the apparatus only one time, then it is not multiplied by 2. Because every time when you record or read, so every time when we use the apparatus, there is an error. That's why the error is multiplied by 2. So example, if I say we measure, but in case of volumetric flask, we just read the one label. That's why for volumetric flask, if I find the percentage error or the sensitivity error, so the percentage error in case of volumetric flask is a volume recorded divided by, sorry, the least count divided by volume recorded. We normally record 250 cm cube multiplied by 100. So that will give us percentage error of the volumetric flask. In case of balance, like if you are using a balance, so what you will do, you will measure the mass of empty container and then you will measure the mass of container with the content in the flask. So first you measure empty and then you measure the filled one. So as we are recording, like example, the mass 1 was 2 grams and mass 2 was 2.5 grams. So what is the mass of the salt which we use? So 2.5 minus 2, which is equals to 0.5. That's a value which we record. But what about the error? Because example, if for a balance is 0.001, so if it's 0.001, divide by value recorded is 5 multiplied by 100. But this will not be correct. Why? Because we read the balance twice. That's why it's in uncertainty. The smallest value should be multiplied by 2. Is it clear, this concept of measuring the percentage error? And if you want to reduce the percentage error, if you want to decrease this percentage error, so we should record higher value so that the percentage error will be reduced. Any doubt in this? So how we can reduce this error in measuring the mass? So using a more accurate balance or use a larger mass. As you can see, if I use a smaller, higher precision, error will be reduced. If I measure higher mass, error will be reduced. I'll share another link once this will end.